Well, what I would like to do is to describe our successful landing of the first single retroreflector on the lunar surface. Next slide. Oh, that's it. The landing of Blue Ghost was successful on the 11th, on the 2nd of March. We deployed our NGLR-1 almost immediately, and then the two observatories in Grasse, France, and Wetzel, Germany, proceeded to try and range to it. The French were successful on this day after the landing, and then the following day, both the French and the Germans were able to get results. These results have allowed us to characterize it and to illustrate that we've successfully met the goals of our observations. Next slide. The lunar laser data. The problem is that the range measurements have a scatter, and for all the retroreflector arrays that are currently on the moon, that scatter is one of the systematic errors. What we're doing here is by putting in a single large retroreflector, we can eliminate that error and result in returns that are limited only by the capabilities of the laser ranging system. The measurements from Wetzel, the measurements from the Apollo station at Apache Point measured the returns from Apollo 15, and they were spread over 177 millimeters. We were supposed to do better. The measurements from Wetzel had a scatter that was only 24 picoseconds, and therefore had a scatter of only with the RMS, scatters of 1 millimeter. And so that fully demonstrates that the single retroreflector allows us to get a significant reduction. It's actually, if we go to the next view graph. Next view graph. Okay, that one. This illustrates what happens with the red curve from the Apollo 15 measurements by Apache Point, and the blue curve illustrates the results of the measurements by Wetzel. It's a factor of 17 improvement, which means there's 17 improvement in the accuracy for a given number of returns. And we go back one. As far as the magnitude of the signal, the cross-section, we did this by comparing the returns from NGLR-1 with the returns from the other arrays. The return from particularly the French indicates that we have met our requirements. The actual values for this appear in two view graphs. I'm sorry. Yeah. That's different than this. Anyway, the measurements from Grasse on the 3rd and 4th of March, when we compared with Apollo 15, this was 100% of the return cross-section or rate of return from Apollo 11, which was our target. By comparing it with the returns from Apollo 11 and Apollo 14, it was 90%. So essentially, we've met our requirements there. The analysis of the data from Apollo or Apache Point illustrated the dependence on the return on the polarization. Our retroreflector, because of things I won't go into, the return depends upon the polarization that is transmitted by the laser. So the design, when it has the design polarization, we get a good return. A single run from Apache Point indicated that we had Apollo 11, but that has large uncertainty. Next view graph. Next one. What is lunar laser ranging? This community does not normally have very many talks on this, and so let me give a brief review of what we do. What we do is we put a retroreflector on the moon, send very short laser pulses to the reflector. It's a peculiar prism that sends the light directly back to the observatory. Send a very short pulse, and we time that. Our current timing is at the level of measuring a few millimeters, as compared to the total distance to the moon. All 5 of the arrays on the moon are currently operational. We've had some dust problems, but the growth of dust is much slower than the growth of laser capabilities. And so they're still working properly. But there is a problem that the moon rotates a little bit if you watch it. That means that we don't know whether the photon, it's a somewhat crude statement, comes from the near corner or the far corner. And so that leads to the scatter. And that's the reason that a single corner reflector is a much greater advantage. Next view graph. As far as results of the past 55 years, we discovered the liquid core of the moon 20 years ago. We've studied the quasi-plastic layer that surrounds the liquid core, measured the distortion of the crust due to tidal effects, the love numbers, and have provided the reference for the 2 cylindritic coordinate systems. Also, in astrophysics, we've shown that the big G does not change with time or local space. In relativity, the equivalent, the weak equivalence principle, we've not only made the best estimates, but we've also shown that the gravity itself falls at the same rate as a piece of lead. Next view graph. With Jim Williams and Dale Boggs at JPL, we ran a simulation of a 6-year campaign and found it depends a lot on the where you put the retroreflectors and where you how the ground stations get better. But this is a summary of the 2 extreme cases, but roughly I would say we expect a factor of 30 improvement of the scientific results that we already have gotten from the Apollo arrays, Apollo and the Lunar arrays. Thank you.